Okay. Okay, great. Welcome, everyone. Welcome to the DESC session. So the science collaboration for dark energy science. So today we'll have a few talks and then we'll have half-hour discussions. So you can also start thinking about topics you would like to talk about during this half an hour. So we'll start with Dominique Boutigny, who will introduce DESC. Just checking on Zoom if everything is okay. Let us know if you can't hear or can see the slides. Thanks.
Okay, hi everybody. So I have been asked to introduce the DESC collaboration. So first of all, I should say that the slides are borrowed from these people here. And so all the credits are going to them. If something is wrong, it's probably my fault. Okay. Yes. Okay, now thank you very much. So here's the state of the collaboration, the picture of the collaboration. It was during the collaboration meeting in Chicago this summer. And at the bottom, you have a picture of the Hack Week. The DESC collaboration is doing several Hack Week every year in order to converge on some very specific point and to make progress on the developments. So DESC is 1,200 members, including 237 exactly full members. And the approach is to combine the 5 complementary cosmological probes, which are the cluster of galaxies, large-scale structures, supernovae, weak lensing, and strong lensing. And of course, the challenge is to reduce the systematics and to understand the remaining ones. If you want to see the requirements, this is inside the DESC science requirement document, and the plan, which is which is updated on a regular basis, is also available online. The timeline is the following. As you can see, it follows very closely the project timeline. One thing that you can remark here is that the data previews 0.2, the data preview 1, data preview 2, and so on will serve as object that would be studied by DESC, and these studies will extend beyond the starting of LSTT data taking. Okay, so the DESC structure is the following. Here you have the organization chart where you have several bodies. So the spokesperson, which are in green here with the deputy spokesperson and the ombudsperson person, are not really the management of the collaboration. They are more here in order to put the holes inside the gear in order to make the collaboration running smoothly. Then you have the Speakers Bureau, publication boards in order to take care about talks, projects, and papers. The policies are discussed within the Collaboration Council, which is a very diverse and broad council, including a lot of several people, including a lot of young people. And of course, there is a working group coordination for analysis coordinator, computing and simulation coordinator, and technical coordinators. The DESC structure, there are three main topics. The first one is are the analysis working groups with all these working groups. I'm going to detail everything. The computing and simulation working groups with science release validation, computing, cosmological survey simulation, and a set of technical working group, for instance, photometric correction or point spread function and so on. And everything we are trying to make all these things to work all together in an harmonious way. DESC computing resources. Computing is extremely important within DESC. So the National Energy Research Scientific Computing Center, the so-called NERSC, is a user facility operated by DOE, and it is the main computing center for a lot of DO projects, and including DESC. So DESC is building a computing environment at NERSC, but where it provides a central place for the collaboration to work together. But it has three secondary computing facilities at Argonne, at IN2P3, and in the UK, which will be available during the operations. And there are also very tight connection with the three Rubin data facilities at USDF, French DF, and UK DF. No. Something changed. No. Yeah. Okay. So one important aspect of at the boundary between science and computing was the data challenge 2. It is an end-to-end simulation of 5 years of observation by the Rubin Observatory, restricted to approximately 300 square degrees. The ingredients are a cosmological simulation of galaxy catalog with realistic galaxy colors, size, and shapes, and shears, and spatial correlation. Realistic supernovae and AGN light curves, which are lensed or unlensed. Simulated what drilling field or deep drilling field survey cadences with realistic observing conditions. Image simulation with as realistic as possible contribution from the PSF from the atmosphere, telescope, and electrostatic effects inside the CCDs, and image processing using the standard LSST science pipeline codes provided by data management. The resulting object catalog are used as input to DESC analysis pipelines, and you have an example here of the area, the sky area, which has been simulated, where you have a tract and patch numbers, and each patch correspond to a coordinate image. And if you are looking inside these coordinate images, you can see a cluster of galaxies. DESC is providing the LSST DESC portal for serving public data associated with the publication about DESC Data Challenge 2. And it also provides the GCR catalogs, which is a very convenient way of accessing the catalogs in order to make plots and to run some analysis on the simulated catalogs. Of course, this is now superseded now by the Rubin Science platform, which is providing access to the DC2 data, which is now which is the input for data preview 0. An example of the static universe with a few image stamps corresponding to various parts of the sky which has been simulated. So for the static sky, and also for the time variable sky. So this is not, in principle, this is supposed to be animated, and you will see this this strongly less AGN rendered over 2 years of observation, which is blinking in not in real time, but in during the two years of observing time. So the DESC science, it can be seen at the interaction between analysis, technical, and computing working group. This is essential for which are essential for DESC science. Most of the DESC science has been based on the DESC data challenge 2. And there are regular science planning goals and deliverable set, which are inside the science roadmap. And all the requirements needed to achieve the DESC science are laid out in the science requirement document, as I said previously. And I will show some example of our analysis effort. I choose two examples. The first, one for the transient sky, another one for the static sky. So for the transient sky, this is the DC2 supernova result, which is an end-to-end test of the supernovae analysis pipeline. And where the question was, can we recover input cosmological parameters, individual light curve over the full redshift range from DC2 images simulation using the LSST pipeline and literature codes, sorry. And the answer is yes. So here at the top, you have one calibrated exposure with some supernovae, and at the bottom, you have the image reference, which has been used in order to detect these supernovae. Unfortunately, on this plot, you don't have the difference image between the two, but believe me, it works. And here you have the signal over noise ratio, which has been of the supernovae, which has been recovered by difference image analysis. And the result is this, which is described in this paper by Sanchez et al., where you have here on the right the Aubourg diagram. And in the paper, it explains that they recover 50% of the events for signal over noise ratio of 5.8 and 100% for signal over noise ratio greater than 8. So it allowed to understand the biases as a function of magnitude, host galaxy, surface brightness, etc. Of course, one of the big important thing here is LSST will need a low-Z anchor sample in order to have a correct Aubourg diagram. And DESC developed the DIA pipe and tools for analysis, which were not provided by LSST DM at that time, and now testing the upstream alert infrastructure. I don't know if it is clear in this presentation, but there is a strong, we're trying to be as coherent as possible with the project and to have as many interaction with the project for this kind of developments. Regarding the static sky, there is a static analysis roundtable called STAR. This is a new initiative starting a year ago, I think, to get all DESC working group relevant to lensing, the so-called 3x2 point, and cluster working together to define all the steps between Rubin data releases and cosmology results. So this initiative was extremely important inside DESC because it allows to develop a lot of several pipelines, which several individual pieces for the final pipeline to determine cosmological parameters. And DESC is planning a series of gradually more realistic joint data exercise. And this is especially during the last meeting in Chicago, there was a lot of discussion around that, and it was, at least for me, it was a real pleasure to see that all the pieces are coming together, and that we are very close to have a pipeline for cosmology analysis, which is working. So here is a chart. Here you have at the top you have the data coming from the Rubin data release. Then there is all the internal reprocessing occurring inside the DESC in order to provide the so-called DESC catalog, including the lens catalog, the cluster catalog, the shear catalog, the PhotoZ catalog, and so on. And then the last part at the bottom are the set of all the pipeline components which are put together, like the 3x2 point TX pipe, for instance, which has been developed inside DESC, the package for the covariances, the package for the on the cluster side for the mass posterior, number-cut histogram covariance, and so on. And at the end, the cosmology inference with Firecrone in order to infer the cosmology parameters. So the summary, DESC is on track to analyze the first Rubin LSST data releases for both the static sky and the transient sky. All the pipeline components are available in a preliminary version, and I would even say in an advanced version, in fact. And now all these components are assembled together and tested in order to create a full pipeline to fit the cosmology parameters. There are many interactions and crosswork with the Rubin project. DC2 simulation is an input for data preview 0, for instance. This is one of the contributions. Several algorithms developed by DESC are passed to DM. This was the case, for instance, for PSF algorithm and for deblending. And there are contributions to sensor data analysis because it is crucial for cosmology analysis. And there are also some planned contributions to commissioning. Thank you. Are there any questions? Mm-hmm.
Hi, thank you for the talk. I think DC2 is a very important thing to testing in preparation for the survey. You mentioned the simulation of the deep drilling field, which is not part of DP0, but could you please clarify what is available on the DESC data portal? I mean, is there a possibility to download the data that have been processed with the LSST pipeline, or is it just raw data that need to be processed some way?
Okay, so first of all, what I DC2 DC2 as an input for DP02 is not the deep drilling field; it's WFD. In fact, deep drilling field turned to be very difficult to analyze. At the moment when we try to analyze the images. For the deep drilling field, we had unsolvable computing problems, which of course will be solved in the future. So that's the first thing. And from the DESC portal, I should confess that I am not using the DESC portal because I have access directly to the to the data. But I think that yes, you can download the data and run your analysis, and you have also access through the GCR catalogs in order to run notebooks, for instance, and to run your analysis. But as I said previously, I think that now this is superseded by the Rubin Science platform. So if you are one of the delegates, you have access to the same thing, and now even better because everything has been rerun with the latest PSF and deblending and a new set of algorithms.
Any other questions for Dominique?
Yeah. Okay. Yeah.
You want to?
Thank you. I posted also on Slack, so maybe you can follow up. So you mentioned, and there has been discussion on this, that DC2 also has the realistic AGN light curves and that they have been simulated, but obviously they are not available. Is there a plan to make them available for the AGN?
I don't know.
Okay.
Does someone know in DESC? I don't know.
Okay.
What I can tell you is that the AGN played a very wrong trick for DESC at the beginning because the curve were completely wrong in the simulation originally, so they had to be re-simulated afterwards.
Okay, so there is a lot of room for improvement.
Yeah.
Okay.
But frankly, I don't know the status. But I will forward the question to DESC and I will get the answer.
Thank you.
I will say for the Elastic Challenge,
Do you have
where
any
we're
question on Slack? Yeah, then, okay, let's thanks Dominique again. And now we'll have a remote talk from Alex Gagliano.
great. Can everyone hear me okay?
Can you send-
Hello, can everyone hear me? Testing, testing. Can everyone hear me okay?
We can hear you,
Great.
and if you can share your screen, we can get
Yep.
started. We see everything. Yeah, great. Okay.
Great. Okay. Hello, everyone. I'm Alex Gagliano. I'm an NSF graduate fellow at the University of Illinois at Urbana-Champaign. I'm really happy to be here today, even if remotely, to talk a little bit about my recent work with a suite of exemplary collaborators. We submitted the paper a couple of weeks back, and the paper is called First Impressions, Early Supernova Classification Using Host Galaxy Information and Shallow Learning. I'll talk a little bit about what each of those components mean and why they're important and why they're relevant to current LSST efforts. Okay, this is a picture shamelessly snagged from XKCD. I think all of us here are very excited about the potential for LSST to revolutionize our understanding of the time domain sky. And LSST is going to be a pretty incredible discovery engine for variable sources like supernovae, but our ability to understand the underlying physics powering these events is really not assured. So if our spectroscopic resources on the whole are not exponentially increasing, actually breaking exponential scaling for LSST, if our spectroscopic resources are not matching this growth, then all of a sudden we're in a tough situation where we have to very quickly prioritize what events to look for based on sparse photometric information. And the potential scientific yield of the phenomena we see is dramatic. I mean, there are lots of things that happen within the first couple of days of a supernova explosion that tell you a lot about the underlying physics and the progenitor system that led to the death of that star. And as we push into this fast and faint space in the kind of time domain landscape, bottom left, we start to see phenomena like shock breakout, interaction with surrounding circumstellar material, shock cooling, interaction potentially with a companion star that tells you you're looking at a binary system. And in the past couple of years, we've also started to discover a dramatic range of different phenomena that we've named tortured acronyms like fast blue optical transients, fast evolving luminous transients. I won't go through all of them, but it's a panoply, kind of a mess right now, as we seek to understand the things that we're looking at. And LSST, it's kind of unclear whether it'll give us a better sense for what these events actually are. But we'll find more of them, which is great. And as we push toward photometric classification of transients, there's been this kind of shift. Of course, everyone is excited about machine learning right now, but we've started to construct machine learning architectures that are incredibly complex. And they offer functionality that you might not get from a simpler model, but you do this at the expense of interpretability. And I should say that these two models I'm highlighting, the first one, which kind of wraps around like a snake left to the bottom, I don't know if you can see my cursor, and the other one, top right, these both contribute valuable insights to the literature. I mean, one allows you to estimate a spectral time series for an event, and another one has what's called an attentional component, which allows you to look at which observations are most valuable in making a certain classification. So these are really useful frameworks, but it has not really been explored to date just how simple you can go with a machine learning architecture and still do reliable photometric classification. And this is what we sought out to investigate. A valuable component in this research was the Scotch catalog, or the Synthetic Catalog of Optical Transients and Correlated Hosts, another tortured acronym. This is a catalog that was produced within the Dark Energy Science collaboration, like Dominique was just talking about, in pursuit of the goals of the Elastic Challenge. Another acronym, the details aren't super important, except to say that the Scotch catalog embeds realistic host galaxy information for many different types of explosive transients for the first time. This was really exciting, and it seems like this host galaxy information could be valuable for classification of supernovae, not just with full phase light curves, but actually early in their explosion when you don't have very much photometry from the explosion itself. So this is data that we ended up using for training our final network, which is a recurrent neural network. A recurrent neural network is just a neural network that has a series of neurons which have gates associated with them, which allow you to filter information as it propagates through the network. And this is really valuable because when you're actively obtaining data, as in the time series, the time domain setting, you're wanting to make predictions in real time, right? So if you have a series of recurrent units, then you can make a prediction with the partial phase of a light curve. And as you get more data in, the hope is that your classification results improve. So recurrent neural networks are a very useful framework for early classification. That's what we ended up using for this system. And we also developed a Gaussian process model that was parameterized by the correlation between observations in both wavelength, space, and in time. And this is a very flexible model. And the value of this is that as you get more data in, because the correlation is observed to tighten between the light curves in different passbands, you see that your model fits improve across all passbands simultaneously. So this was an early test on LSST simulated data, and you can see that the light curve model gets significantly better as you start getting observations in any of the bands. And so our initial tests using Scotch simulated data for LSST light curves. On the left, I'm showing a simulated framework in 2019 from Daniel Unnikrishnan. This is a light curve classifier called Rapid. As more data comes in, you now jump up in classification probability, and the code tells you that you're looking at a type 1a supernova. This is also a recurrent neural network that was used to classify these events. And on the right, we see that with the inclusion of host galaxy information, in this case, we're incorporating derived properties like stellar mass and star formation rate. And we see that even before we have any real detections from the explosion itself, so this is the light curve, here are the non-detections in kind of this noise area on the left, you see that you have a non-zero probability that you're looking at a type 1a supernova from the correlations with the host galaxy. And then as soon as you get photometry in from the explosion itself, your classification probability jumps up and the code says, okay, now I'm more confident that I'm looking at a type 1a. So this was a promising intermediate result, but of course, derived host galaxy properties are not going to be readily available for all of the galaxies, the host galaxies that we observe for LSST. And so we started to push toward a more realistic data set to validate our network on using a couple of different techniques. So one of them was a component called transfer learning, whereby we trained for the vast majority of the training sequence on simulated light curves from within the Dark Energy Science collaboration. And then we retrained the network for a small number of training epochs on observed samples. I'll talk about the observed samples a little bit later. And this allows the network's weights to tweak and adapt in different ways to match the additional complexity of real observed light curves. The second component is that we developed a more realistic model for photometric redshifts. So Alex Maltz, who's a postdoc working with us, was really valuable in generating this normalizing flow. It's a machine learning method, and it allows us to condition predicted redshifts based on the photometric properties of galaxies in the simulation to more realistically match the scatter of photometric redshift estimators working in practice. So the black dots are our photometric redshifts on our observed sample. The green 2D histogram shows the simulations. And so we're trying to more realistically match that scatter. There's still some catastrophic outliers that we find in the observed sample that we don't match, but it's closer to getting the two to agree than we had seen before. And then the third component is that we want to use all of the data available to us, all of the transients, but of course, transients don't appear in nature in equal numbers. So in the observed sample, we ended up tweaking the weights associated with each of the classes in calculating the loss function for training the network. And this allowed us to A, use all of the data, but B, not constrain ourselves to only learning the photometric properties and the host galaxy properties of the dominant classes in our sample. And for the observed sample, we used as a case study the light curves from the young supernova experiment. Dominique was talking about the need for a low redshift anchor sample for cosmology. This is exactly what the young supernova experiment has been tasked with doing. So we've purchased time on pan-stars 1 and 2, and with a 3-day cadence of observations, light curves are generated combining ZTF, Atlas, and pan-stars for a higher collective cadence with the hopes that we would consolidate low redshift type 1a supernovae and better anchor our cosmology. So Young Supernova Experiment, or YSE, YEEZY for short, is a local supernova discovery machine, and it ended up being the observed sample that we used to adapt our network and validate it on real data. And this is kind of the big exciting end result of the approach that we took. Is on the left, you're seeing a receiver operator characteristic curve, which tells you something about the rate at which we correctly identify events as belonging to one of these 3 classes of supernovae as a function of the rate that we get the wrong things, the negative events wrong. So if you're doing well, then these curves should push toward the top left, and the area under the curve better parameterizes how well you do for each of these classes. And area under the curve of 1 is occurring in the limit of perfect classification. So the end result is that you get areas under the curve of above 50%, which would be random classification. This is really exciting because we're looking at the performance just on day 3 of the light curves, 3 days after the events were discovered. And this is the first time that photometric classifiers have been validated on real data showing this kind of performance within the first 3 days. So this shows you that there's valuable information encoded within the host galaxy and within the transient that allows you to reasonably start to distinguish between these events early. And so this was really exciting. This is a very promising result. I don't have time to go into it at all, but I would argue that if you're designing the kind of ideal system for real-time characterization of LSST transients, you would want the system to have 4 properties. 1, you'd want it to be rapidly scalable to accommodate the thousands of nightly events we're going to see. 2, you want it to be context aware to incorporate host galaxy information, like the kind that I was talking about earlier. But you also want it to adapt to anomalous things that you don't expect to see, right? You want it to be able to not just put everything into a box, and you want to still be able to identify anomalous behavior and make new discoveries. And the 4th point that I don't have a lot of time to talk about is I think that it should have a mechanism for quantifying uncertainty in a prediction for either a class or underlying physical parameters. And it could use that quantification of uncertainty to best know what to do next, whether to obtain follow-up, whether to get a better underlying physical model, etc. So I'll end by saying there's a ton of scientific return that we can get out if we're able to do this early characterization of follow-up of different classes of transients. Multi-messenger sources are really exciting right now, not just to find the second kilonovae, but also for lots of different particle sources that we've discovered recently. There are rare and unusual systems that the sky is filled with that evolve on very short timescales that we would love to know more about. And as I mentioned, the first few days of a supernova tell you a lot about its underlying progenitor physics. And so we hope to find them quickly and accurately to obtain relevant follow-up. So here's my final conclusion slide. I would say that contextual information can improve transient discovery when you don't have a lot of information from the explosion itself, but you would hope that the system that you construct could adapt to new knowledge that you don't expect. And thank you all for your attention.
Yeah, thank you, Alex. I think you can hear me.
Yep.
Now we can take a couple questions from the room or on Slack. Are there any? Do you have any questions on Slack? Yeah.
Yeah, can I ask, so what is exactly the time, like the, yeah, how long it takes to, like the application of your algorithm, what are the timelines basically? You know, like how long you have to quickly like associate a host galaxy and like, yeah.
Yeah, that's a great, well, thank you for the question. I appreciate it. There, as you mentioned, are various components. The actual classification from this system is negligible. I mean, training takes hours, but once you have it trained, it's a fraction of a second to actually do the classification. The association with the most likely host galaxy, I mean, presumably this is going to get better as your LSST data gets better, you get deeper coads, but there are current, unsurprisingly, machine learning solutions to doing this that allows you to associate the most likely host galaxy in a couple seconds. So non-negligible contribution to the total budget for your thousands of nightly events, but still feasible to do with all of them.
Yeah, there's a question on Slack. So,
Yes, from Fabio Ragosta. So how numbers of filters available can substitute the host galaxy information on classification performance?
Sorry, I'm not sure I understand the question.
Me neither. I'm trying to pass at the same time, sorry. Yeah, so the number of filters available, can they substitute the host galaxy information on classification performance? So if you have more filters, does it help basically? If I okay.
Yeah, that's a really astute observation. I mean, the analysis of exactly what features are valuable at different epochs, I did not explore. I mean, this whole framework that I've been describing is done with the hopes that you're relying more on the host galaxy information early and then later on the light curve information. I didn't actually do that that type of analysis to see when you would switch. As you mentioned, the thinking is that eventually when you get enough data in multiple pass bands that you would just be relying on the explosion photometry directly. But yeah, more work is needed to see exactly whether that's the case. I should mention that one of these more complex models, the top right one, Pimentel, has this attentional component, and this same framework could be used to look at exactly what features are most important at each phase of the explosion that you're observing. So that's a type of analysis that could allow you to see when you would make the switch between relying mostly on host galaxy information and mostly on the explosion.
Not sure. Yeah, thanks a lot, Alex. Thanks Alex again for his very, very nice talk and discussion. We can follow up on Slack if you have extra questions because it was very interesting. Now we'll have another talk from Simona Mei. If you get the slides. Almost there. Yeah.
So I will speak about machine learning.
Okay, Thanks. I thank you to the organizers for this wonderful conference and for inviting us to speak. And I'm speaking about machine learning for cluster detection. This is a work that is performed with a postdoc that is Stefani Lich, who changed the recent 1 year ago laboratory, and the PhD student Kirill Grishin, who has taken the leadership on the work. So what do we know? We know that galaxy clusters are reliable probes for cosmology, are one of the probes that will be used by LSST, but only if we know exactly their selection function, the mass and redshift. And the standard detection algorithm have typical completeness and purity of 80% at the redshift that are important for the LSST survey, for which we will have many more candidates with respect to the large surveys today, and the cluster masses larger than 10 to the 14 solar masses. So what we wanted to do is to explore if we could do better with machine learning techniques and compare the different selection functions with what is done today. So this is a DESC project. It's cluster detection with deep learning networks. And what we are starting with is using well-known object detection machine learning techniques on DC2 simulations. So we started with first networks, simple networks, and we decided we will go later on more complicated methods. Bayesian networks will give us better estimated uncertainties. And then we will compare our results with other classical methods that are developed in the collaboration. So we started with our group, and then a lot of DESC members joined, among which you can see Dominique, Boutigny, and Marie Paturel, who are going in parallel with us with the support of everybody else. So this is really teamwork. So the first step, we decided to apply a classical object detection algorithm in machine learning, which is called the YOLO, you look only once. And we applied to the most basic case, just local universe, Sloan digital sky survey, DSS. And then second step, we applied it to the DC2 simulations. And this will lead to several papers, or one more papers led by Kirill Grishin for his PhD thesis. And we will compare afterwards our results with other work in the team. So this is a cluster for the SDSS, for example, a local cluster around Z0.3, that is the median redshift of the survey. And this is another cluster that is a bit higher redshift. So the challenge is that we will go from low redshift to high redshift, and as we go to the high redshift, it's more and more difficult, even visually, so also for the machine learning algorithm to recognize a cluster. So what does the YOLO do? Usually YOLO is an algorithm that is applied in real life to recognize a dog from a bike, from a car. It's used for car driving without the driver. And it's based on a deep convolutional network, DARTnet 53, in this version that we're using, is the YOLO 3. And is used for fast object detection in images. So there you have, oops, sorry, there you have objects. The YOLO looks for an object, creates a region around the objects, and segment the map in regions that are occupied by different objects. So what does it do? It splits an image in S by S cells. If there is an object in this cell, then it starts to detect this object and decides in which region is contained. So the region is called the box. So it puts just a box around an object. So there will be a box around the dog, a box around the bike, a box around the car. It was interesting, is also will give you a confidence score and a probability of an object class. So what's the probability that this object is a dog or a bike or a car? And what we do, we keep the boxes with the highest probability, we discard everything else. So this is really the basic algorithm. And we just take the basic algorithm, but instead of looking for bikes, cars, and dogs, we're looking for clusters. So this is the SDSS red mapper catalog projected on the sky. So these clusters were already detected with a standard red sequence algorithm. And we have 26,000 detection more or less. The average redshift is 0.3. And as images, we didn't take all the filters for SDSS because we know that we are looking for local clusters. So combination of colors in G, R, and I are sufficient. And we made composite images with these 3 bands. What we obtain after applying the algorithm is with training and validation. And we obtain a completeness and purity on the last catalogs of more or less 95%. That is pretty good for a first try. And that will be published in a paper led by Stefan that is in preparation, but almost ready for submitting. And this is precision and recall corresponds to purity for precision and recall for completeness. And the detection threshold that is shown here is the probability that the object in a box is a cluster. So depending on which threshold you decide, you change the purity and completeness. And if you want the best cluster catalog, you will go to the intersection of these 2 curves where you have the best completeness for the best purity. So in this case, the catalog will be produced with the threshold that corresponds to the intersection between the completeness and purity and 95%. Now we ask ourselves the question, is this true at all the redshifts that we probe and all the masses that we probe? And as you see, the result is very stable, both with mass and redshift. So we continue to have very high completeness at all redshifts that are good for SDSS, so between 0 and 0.5 more or less, and all the richness that correlate with the cluster mass. So this is more or less goes from 10 to the 14th solar masses to high mass clusters. So how it is pretty good. So red mapper is probably it's one of the best algorithms that are used within DESC. And we really compare well with red mapper in SDSS. So we can really reach purity and completeness that are competitive. And so it's promising to, we realize that it's promising to extend this at higher redshift. So what about LSST? We will go much higher than 0.5. So we applied the YOLO algorithm trained on SDSS on DC2 images. We continue to use the same bands, G, R, and I, because up to redshift Z = 1, that is what will be more or less covered by the LSST. We expected that this color are pretty good to detect the red sequence at the different redshifts. So we used the DC2 full resolution images, and we chose images around the halos larger than 10 to the 14 solar masses to have just bona fide galaxy clusters. And what is interesting about the simulations is that while before we had the color from red mapper that also has his own biases and completeness and purity estimates, in this case we know exactly which ones are the halos, and we can make a better analysis of the clusters that are detected and undetected. So these are first results. So here you see some clusters that have high probability, so 95%, 97% probability to be a cluster. And you see that visually you can also recognize them as a galaxy cluster with the clear red early type population. And what we obtain is super interesting, because even with the DC2 images, when we are extending a high redshift, we continue to keep this high performance, so 95% completeness and purity there you see the intersection of the 2 curves, and now really stabilizing the analysis by really looking into what we have found and preparing the publication. So we have promised an outline of the paper before the summer, but the coming back on the academic year has been a bit rough. So we will do it soon, and you will find it in the channel of in the Slack channel of the project. In parallel, Dominique, Boutigny, and Marie Paturel, I'm going to the next version of the YOLO 4, and they applied again on DC2 full resolution images in the same filters. They already prepared 6,000 images for training and validation, and they just got an allocation of 50,000 hours on the Gen Z supercomputer, so that we will know soon the results. So that our teams can work in parallel and have and compare what we find with different versions of the YOLO to find which one is more adapted to the LSST. Because while now we go on the HALOS and LSST, we will have to work on survey mode, and that means that comparing the performance will be very important in terms of speed of the algorithm. And they also want to extend the analysis to the entire 6 bands in the future. So to conclude, our preliminary results show that for the DC2 clusters with an halo mass larger than 10 to the 14 solar masses in the redshift range 0.3 or 1, we obtain the same performance than as DSS, that means 90% purity and completeness, without retraining our network. So the learning has been transferred in a very efficient way from the SDSS to DC2. And the next steps are to compare the team efforts, so the different groups in Paris and SC, and to optimize the training for the DC2, add an estimation for redshift and mass, and then compare with the red mapper DC2 detection in the same area and with the other cluster algorithm. But with red mapper will be really important because we kind of base the training on red mapper, so we really want to recover red mapper at the best. And this is the end of my presentation. If you have questions, please go ahead. Thank you.
Thanks a lot, Simona. Are there any questions in the room for Simona? Maybe I can get started with.
Hello, very nice talk.
Thank you.
I was wondering, so you are planning to use this algorithm, or obviously LSSC data. So what do you think, what's your impression would the, if you train the algorithm on SDSS or DC2 data and then use the model on LSSC data, would it work the same, or would there be any differences? What's your impression on that?
We were surprised that the transfer was really easy. So we didn't change the weights at all from SDSS to DC2, and it just worked like a charm right away. Yeah. So yeah, so Kirill had to pre-process the data in the same way. So if the data pre-processing is exactly the same, the results are very stable. Yeah,
that's great. Thank you.
Yeah.
And there was another question, maybe on Slack or maybe from you.
From me for now, but maybe there will be one. But will you also, so maybe I have 2 questions. Will you use DC2 also as to train the YOLO for actual data?
We didn't, because the SDSS training worked right away. But while Dominique and Marie are doing their own training independently from us, so that we are completely independent, and then we can compare, you know, on the basis of a different approach. So that Dominique and Marie will train on the 6,000 images. Dominique, correct me if I'm making a mistake, perfect. And while we decide not to train, because I mean, with 95% recovery in completeness and purity, now we think that the priority is not to retrain the weights, but to understand which one we don't detect and why we don't detect them, and what is, you know, how we can transfer it better to the real data practice. And I think also something that will be really important is to go in survey mode, not to center on the clusters like we are doing now, but just taking the entire thing and just cut it in pieces like a real survey. And that will give us the estimation of the speed and efficiency on a real survey, not only, you know, we go from proof of concept to let's do it now. Yeah.
Okay. Thank you. There is a question on Slack from Nushka Chamba. So the question is, do you, thanks a lot for the talk first. And do you have plans to check how YOLO would detect new clusters?
Sorry?
Do you have plans to check how YOLO would detect new clusters?
I don't understand the question. So when we train the sample, we train it on half of the SDSS sample and we validate it on the other half. So we kind of discover new cluster, no, around, yeah. And then we just use the same weights on DC2 without training. So we were discovering new clusters in DC2. I don't know if I answered the question. So that in DC2 practically the cluster were new because we didn't know, yeah.
Okay.
But I don't know if this is the question.
Yes.
Yeah,
so
it is the
you
question.
seem to have addressed
Okay,
the question.
okay.
Yes.
Thanks a lot again, Simona. Ah, there is an
Thank
extra
you.
question.
Okay.
I can keep you 1 extra minute and keep it short. We're running late. Thank you.
Hi, Simona. Thanks for your talk.
Hi.
Looks really exciting. I'm curious if you, globally, the completeness and purity look great. Did you look at the trend of these metrics as a function of redshift? Is there any sign?
So we looked for it in SDSS and there is no trend practically in the local universe.
Shift with at high.
Redshift, Kirill started to do the first plots and he didn't say it to me, so but he will show them very soon to all the collaboration. Yeah. So we have to stabilize the analysis to, yeah. We have to go deeper now.
So, thank you, Simona, again. We'll have
Thank you.
one last remote talk. Unnikrishnan, if you hear me, if you can.
Can you hear me? Hello?
Yeah.
And can you see my screen?
Yeah, if you can share your screen, that would be perfect. Yeah, we see you, so I switch off the mic and you get started.
You can see my screen, right?
Yeah,
Okay.
perfect. So,
Yeah, so hello everyone. My name is Unnikrishnan. I'm really sorry that I couldn't join you in person, but I'm very happy to give this talk online. Thanks a lot for the organizers. So today I'm a PhD student in the Astronomical Observatory of Jagiellonian University in Krakow in Poland. I work with Professor Agnes and Nadur Kalets. Today I plan to talk about the correlations between different galaxy properties and the environment in the large scale structure that dependent that we have observed both in the observations and in the LSST simulations. So we all know that the large scale structure of our universe consists of regions where there are overdensities of galaxies such as nodes, and then also we have regions where there are less number of galaxies living together called voids. So what we know about these galaxies is that they live in the dark matter halos, and the properties of these galaxies are majorly defined by the properties of the dark matter halo in which they live. And at the same time, the properties of these dark matter halos correlate with the environment. By environment, I mean whether they are in the more denser regions of the cosmic web, like are there many galaxies living together, or so it's dependent on that. And hence this prompts a correlation between the galaxy properties and the environment. So traditionally, these dependencies have been well studied using galaxy 2-point correlation functions. Two-point correlation function basically compares the real distribution of galaxies with a random distribution. And for a given scale, it's a function of scale r, which is the separation between the galaxy pairs. And at a given scale, the greater the value of correlation function, it means the galaxies in that particular sample shows a stronger clustering at that scale. So it has been widely used to study how different galaxy properties and the clustering are dependent on each other. So these are a few of the many works which explore this. So for example, here it's like the correlation function measurements for galaxy samples of different brightness in R band. So which tells us that the galaxies which are brighter in the R band, they exhibit a stronger clustering than the fainter galaxies. And on the right plot, the same observation in the terms of stellar mass, where we see that the more massive galaxies tend to exist in the denser regions of the cosmic web. So all these works conclude that the more luminous, the more massive, the more redder and evolved the galaxies are, then there's a high probability of observing them in the denser regions of the large scale structure in comparison to their counterparts. So yes, this tells us that there is a correlation between the environment in the large scale structure and the galaxy properties. But what we are interested in is how are these correlations different for different galaxy properties, like how it is for luminosity, stellar mass, star formation rate, and so on. So for that, we use a tool called the marked correlation function. So it is a function just like 2-point correlation function. It is a function of the separation. At the same time, it is defined for a given property. So to study the dependence, environmental dependence of a property, we can use the rank of that galaxy for that property as a weight to compute a weighted correlation function. So which means that a galaxy in a sample having a higher stellar mass will have a higher rank in terms of the marked correlation function. So using this weighted 2-point correlation function, which is this W of R, and the unweighted correlation function, we can estimate the marked correlation function for a given property at a given separation scale. So this can be used for any property that we are interested in, like stellar mass, star formation rate, and so on. And at a given scale, and for a property, if the marked correlation function is unity, it shows a lack of correlation, and a greater value shows a correlation, and value less than 1 shows an anti-correlation. And the strength of this marked correlation functions can be imply how strong is that property is dependent on the environment. And also we can compare different marked correlation functions from different properties to say which property is strongly correlated with the environment. Now, so using this tool, we have first measured marked correlation functions in the gamma data. So gamma is a spectroscopic survey with galaxies fainter till 19.8 in R band. So from gamma, we have first selected a sample of galaxies with the selections given here with redshift cuts and mass cut, and then measure their marked correlation functions for different properties. So this on x-axis is a separation scale, and on y-axis is the marked correlation function, where the circles, for example, this one, it shows the stellar mass marked correlation function, and others show these for our luminosity marked correlation functions in different bands, like K to U bands. Then we have star formation rate and specific star formation rate. So the interesting thing is that this signal varies for the same set of galaxies. So if you measure the 2-point correlation function, you get one correlation function. But when different weights are applied, then these different signals is what we observe. And this actually helps us in checking how the subtle difference between different galaxy properties exist in its dependence on the environment. And from this, we can see that the stellar mass marked correlation function, which is the one which is strongly with higher amplitude, which means that it is the one that is strongly correlated with the clustering. At the same time, star formation rate is in the opposite way. It is, which means it is anti-correlated. Also, when we look between different luminosities, we can see that the K band, this one, K band is the one which is close to the stellar mass, which means that K band luminosity's dependence on the environment is similar to that of stellar mass. At the same time, as you go to further bluer bands, it changes, and then the U band, it is similar to the star formation rate. So this is also so basically we use the K band as a proxy for a stellar mass because of its sensitivity to the radiation from the evolved stellar population. It can be a good proxy of stellar mass. But when it comes to the clustering studies, if we use K band selected sample as a proxy for stellar mass selected sample, we can get a closer behavior between each other, but then we still see the gap between these Mark correlation functions, which means that they are not perfect proxies of stellar mass. The same applies for U-band luminosity. So in this work, we did only the optical to near infrared bands. And then later in the next work, which is currently under review, we use the WISE bands, the mid-infrared bands of WISE, where the W1, W2 bands and with 3.4 and 4.6 micrometers, then W3 and W4 with 12 and 22 micrometers. So here what you see is this one is the stellar mass, the pink one. Then we have the star formation rate, the gray one, and the W1, W2 and K band, they are similar to stellar mass in its Mark correlation functions. At the same time, W3 and W4 are mimicking the star formation rate in its clustering behavior. So this also tells us that even the mid-infrared bands are not perfectly correlated with the stellar mass or star formation rate in tracing the environmental dependence. Now, also we use Mark correlation functions to check how the survey limit, flux limit influences the clustering measurements. So for instance, this is one set of galaxies selected from gamma in its redshift and mass distribution plane. And this is all the galaxies with a flux limit of 19.8. Now we imposed a flux limit of 17.8 to check how the sample varies and hence how the clustering signals vary. So this is the one. So when we impose a flux limit of 17.8, which is a brighter cut, then we lose many galaxies. If you compare this red and green plots, you can see that when this flux limit, imposed flux limit, took away a lot of galaxies, almost half of them. And this is the comparison if this affected the clustering signal. So sorry, the plot is a bit busy, but I'll try to explain. So this, again, the x-axis is the separation, and on y-axis it is the ratio of these Mark correlation functions for different properties between the brighter and the fainter cuts. And almost everywhere we do not see a significant difference, but yet we have scales in which these ratios are significantly away from the unity, which means they are affected. Now we wanted to do this further, go further in the study with much more brighter flux limits, but unfortunately gamma had limitations in its number of galaxies, which in those limits, which is actually important for clustering studies. So in that's the time when we expect that LSST can be of really can be helpful. And as a as a first test, we checked how well do the LSST simulated catalog, the Cosmo DC2 simulated catalog, can be useful in these studies. So for that, we used the Cosmo DC2 catalog. So from first, we checked whether Cosmo DC2 catalog, it shows the well-known stellar mass dependence of clustering. For that, we selected galaxies which are binned using stellar mass, as you can see in this distribution plot, and then compared their 2-point correlation functions. And you can see the result here, where the correlation functions which assumed to be a power law we have the parameters of the power law fit here, and where R0 is a quantity that tells us how stronger the galaxy sample is. And then as you go from red to blue, the more massive the samples get, as you can see in the legend, and which means that the massive galaxy sample is more clustered here. So it is fine. It is well known, agreeing with what we observe in data. But when we use Mark correlation function for different properties, do they agree? So for that, we selected 2 samples from the observed from data gamma and DC2 with the same selection cuts. So you can see here same selection cuts for both the samples. So ideally they should behave the same, but we do not. Let's see if we see that on the left panel is there 2-point correlation functions, with the red one being for the DC2 and the violet squares for gamma. And we can see that even for the same selection, gamma sample shows a stronger clustering than DC2. And on the right panel is a Mark correlation functions for U, G, R band luminosities and stellar mass, with the shaded curves for the gamma and the markers for the DC2. And okay, we can see that this DC2 Mark correlation function, they still preserve the hierarchy of the Mark correlation functions that we observe in the data, with the stellar mass one being stronger than others. However, for a given property, the Mark correlation function between DC2 and gamma, they significantly vary, and this is something that we have to study further, like why is that happening, why we do not see agreement in their clustering behaviors of different galaxy properties. So now we also ran a trial with exploring the flux limit, influence of flux limit, and this is what we saw earlier, the ratio of brighter and fainter flux limits, Mark correlation function for both the flux limit, and we see the same effect in DC2 but in a different way. So this is a preliminary result and would like to explore this further. So I think I'm almost at the time, and I'll stop here with the conclusions. Thank you.
Unnikrishnan, are there any questions for you in the room? Yeah, there's one.
Thanks for a great talk. I was wondering how I should interpret your environmental measures. What kinds of environments are you tracing in your gamma data? Do you go from clusters to the field, or are your richest environments groups? So I'm just trying to get a feel for what kinds of environments you're actually tracing.
Okay, so we do not classify into different groups, or we do not check whether they are in clusters or like voids, but we are statistically checking whether they are in denser or less denser environments. For example, if you have this separation here and you see the greater strength for Mark correlation function. So this is basically a probability of finding galaxy pairs separated by this separation. In this pairs, both the galaxies are equally massive or luminous. So which means that we can find a greater probability of galaxy pairs separated by this separation scale, with both the galaxies equally brighter or massive. So which gives us a scale independent probe of the environment. We do not we do not have to classify into different environments. I hope I answered that.
Yeah.
Thank you.
Thank you. Is there any other question? Yeah, maybe one on Slack. And I think that will be the last one because we're.
Okay, I just wanted to ask a question. So I think that's very interesting, the difference between gamma and Cosmo DC2. So have you tried, so you said you were going to investigate, but have you tried on other simulation to see if it's, to see what would be coming?
Actually not yet, but that is in my plan to do, but I haven't done that yet. Yeah, it will be the next step to check how it is, why is it happening. Yeah.
Okay, thanks a lot. If there are no pressing matter, I send you on Slack to pursue the discussions. Thanks a lot, Unnikrishnan, for the very nice talk and answering. We'll now have a general discussion in the room around dark energy science collaboration. I don't know, you wanted to get started?
Yes, thanks again to all the speakers. So first of all, I wanted to see if anyone has attended the DESC sprint last week and was willing to maybe just give some quick summary of what went on. Sorry if a bit on the spot, but just in case we have someone. Yes, François, feel free to unmute. François, can you hear?
Hi, everyone. Can you hear me?
Yes, we can. Thanks.
Fantastic. So very quickly, last week was a really fantastic week at University of Michigan. We had 13 participants working on over 30 different projects and 30 remote participants joining us. And we had a lot of activity across the board on all topics on the science collaboration, and especially topics related to getting ready for processing the data. Happy to answer specific questions, but yeah, it was really fun.
Great. Thanks a lot, François. Are there any questions about that? Okay, then we might come to that later, but I also wanted to give a chance to people who are new to the collaboration, who want to talk about their ideas or their projects. I know there is Andres online. I think you wanted to talk about something, and then we can go through other people. Andres, can you hear? Are you online? Actually, I don't know. I saw him online earlier, but he's not here anymore. Yeah, anyone who is new who wants to talk about their science, their project? No? Okay. So maybe following up on what François was, Nushka, do you want to talk?
Yeah, I wouldn't mind. Thanks a lot. I'm one of the remote participants. I'm also part of DESC and Galaxy Science Collaboration. And I just wanted to briefly mention that one of the topics that was not covered in the DESC session is low surface brightness astronomy. And that's an interest that has been growing in DESC. And my DESC project is actually sort of trying to bridge those two topics. So I just wanted to briefly mention because I'm not there. And there would be more discussions of that topic in the low surface brightness session that's on Wednesday. So if people want to talk to me more about that project, I'm around and I'm on Slack. So happy to discuss.
Fantastic. Thank you so much. Will?
Can you hear me?
Yes.
Did that unmuting work? Okay, good, thank you. Yeah, also in the vein of people that might be new to DESC, can somebody in DESC say a couple of words about where new DESC members may find the projects that are currently underway? Does that actually exist yet? I know some of us have been chatting about this, but it might be nice to have that stated. If there is a resource already for new desk members to find out what's going on.
Yeah, great points. So we use Confluence. So I think there must be a Confluence page. Does anyone has more detail? And we can post the page on Slack. François?
Yeah, so indeed, all the projects in DESC are tracked through Confluence and like a specific database that allows us to track announced projects, their status, progress, and any papers that are associated with them. So it's actually fairly easy to get started, and I can post the link on the Slack for people already.
Great, thank you. That would be great. Nushka, is that an old hand or a new hand? Nushka, can you hear?
Sorry, yeah, it's I just wanted to add to what Francois said, because I'm also a member in DESC, and it is actually really nice that there is a whole list, but I don't know if everyone has access to that list, because I don't know if you need a specific account and you need to create an account, and I don't know if that needs to be approved. So just I'm not so sure about that. And I think some of the other collaborations also have lists of projects ongoing. And one thing that I wanted to mention for the new DESC members, if there are any in the room, is that it's also not so hard to create. If you have a project that's going on and you want to propose it, a DESC, I would say, has a easy way of creating a form and then writing about it and then getting interest. I mean, I had to do that process as well when I started out. So all of that is in the Confluence. But again, I'm not so sure if that is accessible to everyone unless you join as a member. So maybe the organizers can clarify that.
Yes, thank you for explaining. And I think everyone who is a DESC member has access to the Confluence page and the project list. And yeah, definitely. So it's easy to propose new projects. You just have to talk with your working group conveners and get involved in the science. Yeah, definitely. Thanks. So speaking of getting involved in, was there a question over there? Oh, okay, yes. So I just wanted to follow up on one bit of the slide from the introduction by Dominique that was saying that there is a lot of opportunities for contribution, and especially relating, I think it was to the STAR challenge and getting all like the more and more realistic data, getting it started. So I was wondering if you had anyone had more details on where we can contribute. I don't know, Dominique, if you have like, are there big topics in this challenge, or like getting more and more realistic data where people can join the
it's difficult to answer to this. I think there are many opportunities here, and I think that I realize that it's true that a list of projects is probably something which is not public, as you said before, and that's a pity. I would say I think that the Slack channels are completely open. So maybe that could be a way of getting some information, but maybe there is something missing. I will discuss that with Catherine. But regarding the STAR channel, I think there are so many things to do, and I am absolutely sure that any newcomer will be embedded within a week. Sorry for not answering more.
No, I think that's great. Yeah. That's great to know. And I think if anyone is interested, they should contact, I think it's Chiwei, Chang, and Josuns. That's right. Yeah. So we can go to the next comment, I think, in the back. Sorry.
Thanks. I just wanted to advertise the Strong Lensing Science Collaboration session on Wednesday afternoon, same time, but on Wednesday. We collaborate very closely with the DESC Strong Lensing topical team. We're more or less the same group of people, so I encourage people to come along and find out more about the strong lensing aspects of DESC, also known as a collaboration with SLSC. Thanks.
Great, thank you. Yeah, definitely. We should go to learn more about strong lensing. Okay, any more questions or comments in the room, on Zoom, on Slack? Dominique?
Yeah, Dominique.
On a completely different topic, I see that Leon is here, for instance. So I had a question in mind. In fact, DESC has been very much involved in the things related to ribbon computing since a long time. So we have produced DC2, and gosh, it was really, believe me, it was really complicated. I mean, from the computing point of view, not only, but the computing part was extremely difficult. And so my question is, how do you see the future of the collaboration between DESC and the project regarding to computing, regarding to algorithms, science algorithm? DESC, mostly DESC, has developed the new PSF, the PIF algorithm, for instance, which is now part of DM. The deep blending also is, I think that the work started in DESC. So how do you see the future of this kind of collaboration and of the interaction between DESC and the project?
Hi, yeah, thanks, Dominique. Yeah, I know that DC2 was certainly a mammoth effort for the DESC, and we are very appreciative of that. As most people know, we've used that for DP0, and it's been excellent to have that wonderful data set to work with to start to test our algorithms and to test the services. So very grateful for that. For the future of the collaboration, you mentioned, I'll just sort of divide it into two things. You talked about computing, and you sort of also talked about algorithms and the collaborations. They are very related. And there are quite a number of collaborations going on with algorithms at the moment, like cell-based coads, for example, and PSF estimation. And I'm going to stop there and ask if Yusra is in the room. She is. I'm going to hand that one over to Yusra. Since Yusra is the head of algorithms and pipelines, I'll let her talk about the specific algorithmic collaborations.
I ran over there then. Thank you. Okay, thanks, Dominique, and nice talk. So you mentioned PIF as an example, and a lot of the algorithms that are being used in DESC were also developed from the dark energy survey, and there's a lot of overlap in the actual humans that wrote the algorithms for the dark energy survey are writing the algorithms for the Rubin LSST science pipelines and are writing the pipelines for the downstream processing that DESC is going to be doing for the science analyses. Tomorrow during the science pipelines talk, I can talk about this a little more. There's the level of there's a shear estimation pipelines that we are committed to being able to support with our coads and our PSF models, but there's no one science pipeline that will perform and do everybody's science, and so we have to do some trade-offs on what we can include in the default data management science pipelines. And when we do those trade-offs, we're going to prioritize the parts of the pipeline that are closest to the camera, like instrument signature removal. Yeah, so did that answer your question? I know
relationship between the DESC pipelines and the data management science pipelines. There's a lot of permeable, it's a permeable membrane, and we're going to be collaborating closely in the future.
Okay, thank you. So yeah, yes, it's partly answer to my question. In fact, my question is triggered by the fact that I am very worried. I am very, I am getting older. I tend to be more and more worried. And in fact, my worry is that if we are not very careful, there will be a tendency, and I can start to see the beginning of this tendency of redoing things. I mean, this is very easy for DESC or for other science collaboration to start diverging from the project. And I think this is extremely dangerous. So I know that DESC has foreseen to reprocess of the order of 10% of the data from at the pixel level, which I can understand, of course, because DESC has probably the most stringent demand on the quality of this processing. But I think that there is a risk that science collaborations start to develop their own pipelines, and I think it would be terrible. So it's more a question, to ask how the project, what the project is going to put in place in order to avoid this kind of situation, and to be able to include the work which is done in the collaborations, in order to become part of the standard pipelines, or to put the thing in place in order to have the right level of exchange between the collaboration and the project.
What I'll say to that is that if you have to do some image processing on the coads or with the PSF models, with the data products, that doesn't scare me. I think that you all are a very creative bunch, and we'll think of image processing algorithms that will support science that we have not thought of yet. What would worry me is if you have to redo instrument signature removal. And instrument signature, it will improve continuously from data release to data release. We saw from DESC, the biggest improvements to getting the precision that they wanted from their shear measurements was in instrument signature removal. And so we expect it to evolve, and I would expect people to be continuously trying new things, tweaking config parameters, testing new brighter, fatter kernels, stuff like that. And then we can incorporate those into later data releases and slowly improve the default pipelines as we move along.
Yes, thank you for these super important points. And yeah, that's really clarified a lot. So I think we'll stop here. I think, Nushka, you had another comment, but if you want to post on Slack, that'd be great. So yeah, thanks again to all the speakers, to Cecile, Eric for moderating, and thank you to our computer person. Okay, great. Thank you, everyone.